Hi, in this video we are going to talk about two main binary search tree related operations, the insertion and the search. So what about the insertion? We start at the root node, and if the data we want to insert is greater than the root, then we go to the right. If it is smaller than the root node, we go to the left. And basically this is the most important principle when we are dealing with binary search tree insertion. So, we would like to insert 12, and because this is the first item we would like to insert, it's going to be the root node. Then we would like to insert 4. We consider the root node, 4 is smaller than 12, so we go to the left, and because there's a null, the 12 doesn't have any left child, the 4 is going to be its left child. Okay, what about the 5? We come to the conclusion that it is smaller than the root node, so we go to the left. But it's greater than the 4, so we go to the right. But the 4 doesn't have any right child, so we insert this 5 to be the right child of 4. What if we would like to insert 20? It's greater than 12, so we go to the right, but because 12 doesn't have any right child, the 20 is going to be its right child. What about if we would like to insert 1? It's smaller than the root node, so we go to the left. It's smaller than 4, so we go to the left and we insert the 1 there. Okay, so basically this is how we built up a binary search tree. We just have to consider nodes. If it's smaller, then we go to the left. If it's greater, we go to the right. Very simple. What if we would like to find the 5? Okay, we start at the root node again. It is the 12. We come to the conclusion that the 5 is smaller than the 12, so we go to the left. We come to the conclusion that 5 is greater than 4, so we have to go to the right. And basically this is the item we are looking for. So on every decision, we discard half of the tree, so it is like binary search in a sorted array. And that's why this find operation is going to have logarithmic time complexity, so ordo log n. What if we would like to find the smallest node? We just have to go to the left as far as possible, and it will be the smallest item, because this is how binary search trees are defined. The left subtree is smaller than the root node, the right subtree is greater than the root node. So if we go to the left as far as possible, then it's going to be the smallest item in the binary search tree. Okay. What if we would like to find the largest node? We just have to go to the right as far as possible, and it will be the largest. And again, because I don't want to repeat myself over and over again, but it's very important that why is it good to construct a binary search tree? Because we come to the conclusion for linked lists that, okay, if we are looking for an item, we have to iterate through all the list in a sequential order, and that's why the search operation for a linked list was ordo n, so linear time complexity. And we had the intuition that, okay, maybe if we use binary search, like we have used it for sorted arrays, then the search operation will be reduced to logarithmic time complexity. And basically, building a binary search tree is something like a sorted array. We are able to discard half of the tree data on every iteration, and basically that's why the final time complexity will be logarithmic for all of the operations. And it's very important that binary search trees have the logarithmic running time for every operation. So we don't have to bother about, okay, what's going to be the application like? Will we have to make several insertion, or will we have to make deletion from the beginning of the array or from the end of the array? We don't have to bother about it. We know for certain that for a binary search tree, all these operations have logarithmic time complexity. So it's very good data structure. Thanks for watching.